Hi everyone, good afternoon. So let's start today's class. So as usual, I will first recall whatever we uh, whatever we learned in the previous class. So I will and the expected utility theory or the VNM expected utility theory is the backbone of classical game theory. So let me go through those axioms again, and uh, those axioms are the basic assumptions that must be hold for anyone to conclude there exists a expected utility theory. So first two axioms, as we have seen, is related with decision in certain situation under certainty. One is the completeness, that means if I present you multiple options and if I present them pairwise, then you inside yourself or you are able to prefer one item over another, or you may feel that two items are indifferent in your preference. uh, so these kind of relations should be each and every pairs of those among those options. So then I can say that these options are complete in sense of preference. That means I can assert a preference among any two options. That's why I can say that these option sets are complete in sense of preference. And second is the transitivity. So if I present you at three options or multiple options, and if the preference relation is transitive, that means if I present you three options, suppose apple, banana, if I present in front of you, suppose apple and you apple and banana, you will prefer apple over banana. And if I present in front of you banana and grapes, you prefer banana over grapes. Now if I present apple and grapes, if transitivity holds, it means apple is preferred over banana, banana is preferred over grapes, then apple should be preferred over grapes. If these three relation holds together, then we will say that apple, banana and grapes are uh, the preference among them are transitive in nature. So this is the thing. Now after that situation, we have introduced, or we have talked about the other sets of axioms which are equally important for establishing expected utility theory. Those are the axiom, those are crucial for decision making under uncertainty. And we have introduced a concept of lottery, and we have we have learned in the previous class that any situation, any uncertain situation whose uncertain state can be represented by lottery is equally represented, can be represented by probability. Any uncertain events whose events are categorized by the probabilities, then those uncertain events can be equally represented by a lottery. A lottery can be two types: simple lottery and compound lottery. And using this lottery, we have another four axioms. One is called continuity. If there are three options are there, so a1, ai and here, then if ai in the preference, if you're in the preference ai remain intermediate between an and ar, then ai can be means if ai is shown to be indifference between a lottery of A1 and AR, and the probability with which this most preferred item you will get as a prize UI can be think as a utility for the particular options AI. And after continuity axiom, we have seen that independence of irrelevant alternatives. That means if I add many more options to your preferred item, your preference will not change. Suppose here, when ai is indifferent to ai to a lottery getting from the continuity axiom, and this preference relation will be uh, remain so if I make a lottery by putting irrelevant items with equal probability with both of these two options. So that means if I make a lottery with p1 probability as a prize a1 I will get, with p2 probability as a prize a2 I will get, and similarly with pi probability ai prize I will get, and pr probability ar I will get. Similarly, if I here also add here, but had the similar option with similar probabilities. However, I add here that what is indifferent with ai and ai tilde, that is uh, with pi probability I add here ai, and with pi probability I add here ai tilde. Now, irrespective of the fact that many more options are added as a irrelevant options alternative added as a prizes, then also these indifference relation actually holds for ai and ai tilde. So this is called IIA, or independence of irrelevant alternatives. Then comes the transitivity. Here the transitivity is nothing but the same concept as we have presented in the case of transitivity of decision making under certainty. Here only the case is we make sure that this transitivity should be as should as well presented with the case of when instead of certain option there are multiple lotteries. If there are multiple lotteries, then among those lotteries the preference should also be transitive. So this is another axioms. And now the most there is another important axiom is called the monotonicity. That means if I present you two lotteries, and each of these lotteries are contain same two options as a prize here. So here if I make a lottery of a1 and ar with some probability, and again I am I am making a lottery with another probability p prime and 1 minus p prime, then if I present them in front of a subject and ask the question which lottery that subject should choose, and which lottery should means if she follows the probabilities rule, then which lottery that individual should choose among these two, then one can easily see that uh, that subject should choose the lottery in which the probability of occurring most preferred outcome is higher. That lottery should be chosen by the subject. Here that means the lottery this lottery will be preferred over this lottery if and only if the probability of occurring the most preferred outcome P if it is greater in this lottery. So this is monotonicity. Then we have proved that if this 6 axiom holds, then we can write using the utilities coming from the continuity axioms, we can write a expected utility, and we can show that this expected utility can truly present the preference among two lotteries which involve multiple options. And this is that, and we have proved that there exists that a lottery means a utility of a lottery will be greater than equal to of utility of another lottery if and only if this lottery L is preferred over L prime. Then we say that there exists a lottery UL, exists a utility UL for L, and we have shown that there exists a expected utility for a lottery. Now, and we have also seen that, or the way we have presented the axiom is called the presentation of von Neumann Morgenstern way. So von Neumann Morgenstern in their book for the first time introduce this concept and prove that the existence of this utility theory, and if any agent's preference are consistent with these 6 axioms, that agents is called the VNM rational agent, and we will say that agents are taking decision as if he is maximizing its VNM utility. That means he is rational in sense of VNM expected utility theory. Now, this is what we have learned, and then we have also learned that many individual in actual real world, people often fail to follow the axiom of VNM utility, axiom of VNM expected utility, and their as VNM expected utility suggests that their preference are deterministic. Rather, in real world we have seen that individuals preference rather stochastic, and that stochasticity can be represented through not through VNM rational way, but the procedural rational way or bounded rational way. And we have seen that with the help of the how that Osborne and Rubinstein in 1998 mathematized the idea presented by Simon, and we have seen a model of stochastic which can truly represent the stochastic preference. It is called the procedural rationality, and we have seen that how a procedural rational agent choose one option among, if I present two lotteries, how that subject choose among between these two lotteries, how he first samples each lotteries either by realizing the outcome of those lottery if she knows the probabilities with which the outcomes occur, or she asks a friend who has a prior experience associate with the lotteries, and she will use those experience to associate a number with those lotteries, and that's why she will choose a lottery. And if she asks a different friend, then maybe different friend her choice maybe depend on her sample, and since lottery is probabilistic and uh, so as her realization, so if she use very few samples to judge a lottery, obviously her sample will lead towards a stochastic choice. So that we have learned in the previous class. Now let us introduce a new concept. It is normal. Today we will learn a normal form game. Normal form game. So up to now we have studied decision making of an individual. However, any individuals who lives in society or lives in group, or as for case of our lives, humans life, or you may radically uh, give an example of ants who lives in a colony, and for those creature also, their decision making does not decision making of group living animals, including humans, in, including humans. So decision making of group living including humans not only depends on our own decision, but the outcome intertwined with the decision of all individual present in the situation. So as I am talking about the example of ant, so let me give you an example of a this is called the strategic, and this is equivalently called a strategic situation. Strategic situation. Now let me give you an example of ants in strategic situation. Okay. So as in our daily life, we have noticed multiple ants, a group of ants together, a group of ants together kill or subdue a larger prey and collectively they are taking the prey to their nest. So this is a prime example. So a group of ants together subdue a larger prey and collectively they are taking the prey to their nest. This is a this could be an example of a strategic situation. Why this is a strategic situation? Because for strategic situation we require that more than one individuals are taking decision together. Obviously here when a group of ants together collectively carrying, we only focus on this collective transport of these ants. So when they are collectively taking the prey to their nest, obviously more than one individuals are present. So more than one individual are present here. More than individual present first, and second is their outcome is intertwined or not. So for let pause for a moment and think about the situation little bit. So so if in your daily life if you carrying some larger item or collectively transport something, you may feel that what a lucky animal human beings are for being gifted by the human language, because using the human language we can coordinate with each other and such that we can we we can and coordinate our action by using the language while the carrying the larger object to their destination. However, this luxury by and large is not present in ant system. Present with the ants, ants ants do not have a advanced language that we human that 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 we have. So how do they manage to carrying such a larger object is a another interesting question. But now let's focus on one particular thing, that only one particular thing, that they may either every individual may either exert a force on that larger prey item towards the towards their nest, such that the whole item get a velocity towards the nest. So they may either all pull or larger of them pull or push or exert a force which in a some coordination manner, but not in random coordination manner. They have to push or pull the prey item toward the nest. And another thing what is possible, they this is pushing towards, this is the action in exerting force toward the nest, and another action will be random. They may everyone may exert force exert force in random direction. So if they exert force in random direction, then the prey item, rather than achieving a velocity toward nest, it will its motion will become like meandering, or like it will become a random motion. Random it will become a random motion, and the time it will take to reach will become significantly longer. Significantly. And natural, it is very natural to assume that, and ants do not like their prey items is uh, do not like meandering with their prey item, and rather than taking their prey item to the nest as quickly as possible, because to do not to pull in the random direction, and the prey item will go as random, it will require a lot of energy and lot of time. So they certainly prefer uh, not to be in be in random motion with this larger prey item. So this is a perfect example of game. Now let us introduce how we can, since uh, so this is the game, this is actually strategic interaction, and this strategic interaction is can be in mathematical term, it is called game. Now why we need some mathematical uh, theory when we can say it verbally? The need for mathematical theory is that verbal description of the situation, as I am describing the situation. So verbal description of the situation is very long, and it becomes imprecise. How means how many word I will use, but it will not become as precise, as if I would if I would presented it in terms of mathematical language. And also, in if I present in terms of mathematical language, it will become precise as well as very short in this description. So let and the mathematical theory that will model, that actually models the strategic interaction, is game theory. Now we will see game theory. And game the strategic interaction or game, a game can be represented in mainly three ways. One is normal form game. Let me recall. One is normal form game. Normal form game. Normal form game. Second is extensive movement. And third is presenting it in terms of characteristic function. Characteristic and in this lecture we primarily or exclusively cover the normal form game. So let me describe the above discussed situation of ants collective transport in terms of a normal game. So first, okay, I will present in terms of normal form game. Before that let me introduce the what is the definition of a game, that is not what is a game. So let me first mathematically make it mathematically precise what is a game, then I will introduce the and this I will present the AND situation with the game and why. Then you can see why I am saying that the above described and transport is a game. So what is a game? I am using the definition given by Martin J. Osborne in the book An Introduction to Game Theory. So a game with ordinal preferences consists of three components. One is a set of players. Second, for each player a set of actions, and third, for each player preferences over the set of action profile, that is outcomes. So a game is defined by any situation which has three components. One is a set of action, a set of player. Second, for each player a set of actions. Third, for each player the preferences over the set of actions, action profile or set of outcomes. So first let us discuss the why the collective transport of the ant is a game, and then the next question is why the collective transport is a game. So first let us check, does it contain a set of players? Yes, more than one and more than one and is involved. Involved in the collective transport. First component is there. Second, does there are for each player, so there are multiple players are multiple ants. For each player there are a set of action. Yes, a set of action. What is the set of action here? So if I reduce the set of action, I can say that first is exert force in the direction of nest, and second exert force in the random direction. So yes, at least two set of action is present for every ant. And third, is there preferences over the outcomes or each set of profiles? Yes, obviously, if suppose everyone are exerting force towards the their nest, so this will be their every, suppose 1 2 3 4 5 ants are there, 5 are exerting force toward their nest, then the larger play item will quickly reach to the nest. So obviously this is the most preferred item, most preferred action profile, and the least preferred will be everyone are exerting force in random direction, and the other are the intermediate among, so they will likewise, but we know that there exists some preference among them. So yes, obviously the third is also be satisfied, then the situation is a game. Okay, up to now it is clear. Now we will present a game in normal form as we have discussed. So let us present the game in a normal form. Okay, so here for simplicity let us assume that only two ants are present there. Assume only two ants are taking the food to the nest. Okay, so two players are there. So this is the set of the players. Let name the player 1 and player 2. Player 1 and player 2, first and second. The action set. So here also we assuming that every player has identical action set, so we have to write the action set of player 1, player 1's action set. We are saying that only two actions are there, either pulling it toward the nest. By n means I am indicating by n the direction of exerting force toward the nest, and by r I am representing that they are exerting force toward in a random direction, player 1, and similarly player 2's actions are an same n and r. And what are the outcomes possible? So let me outcomes may be both of them are, so these may be one outcome n comma n, where the first element is the action of player 1 and this is action of player 2. So similarly this is one option. Another option may be player 1 in, player 1 exerting force towards the nest, and another one exerting force towards the heart. Similarly Rn, player 1 exerting in a random direction, player 2 in towards the nest, and both of them exerting toward the. These are the outcomes. So can we get a preference among them? Yes, obviously it is very obvious to get a preference among them. It is this narrow or not narrow that both of them exerting force towards the nest should be most preferred, because in this situation the food item will reach to the nest very quickly. So first item will be preferred and less effort they have to give to take the food to the nest. Then this is least preferred, this is most preferred, and if both of them pulling in random direction, then the longer time will required for taking the food to the nest, and it will require a lot of effort. And we are assuming that both of these outcomes, nr and rn, is equally preferred, so we will write it as, and obviously they are the intermediate one. So these are the preference relation. Now can we associate utility with this preference? Obviously we can, because as we know from the two axioms, one, the transitive, the completeness. So completeness is follows, which we can readily see from here, and second is the transitivity, and we can obviously see the transitivity is also followed by this. So nr is equal to rn, so transitivity is followed by this. So first you see transitivity means any three item you pick. Since Nn is greater than Nr and Nr is indifferent to Rn, so that means Nn should also greater than to Rn, so that is obvious. And similarly you check pick any 3 among them or any 4 among them, you will see that the preference among them are transitive. So since completeness and transitivity is followed, we can associate real numbers with them to make it utility. So let us write the utilities, or it is equally called the payoff function. Sometimes it is called the payoff function, or it is called utility. So we will synonymously use the payoff function or utility. So utility for player 1 of this outcome Nn, let's put a number 1. So why I am putting a number 1? Because it represent the preference among the outcome. So that's why let me in R we put 0.5, U1 RN 0.5 and U1 RR is 0. So you can see that this utility function or the payoff function actually represent the preference of the player 1. So that is what so that means this is a true utility function, or you can represent by this number. And here it is, we haven't said it explicitly, that the same preference should also be associated with, or the same preference of the same preference, the if you means you should keep in mind the preference is same for player 1 and player 2 here. So the similar utility or the same utility we can also write for the player 2, comma n is 1, u2 n comma r is 0.5, u2 comma n is 0.5, u1 r comma r is 0. This is the payoff function. So now this is a game. Now we are ready for writing a normal form game. Normal form game represented in the tabular form. Tabular. So suppose this is the player 2's action, player 1 action. So player 2's action, we will write the player 2's action in column wise. So player 2 has two action. One is exerting force towards the nest or in a random direction. Similarly, the player 1 has two action, that either exerting force toward nest or in a random direction. If both of them exerting force toward nest, the player 1 utility will represented by 1, or their food will reach to this nest, and that is represented by 1. In the either way you can say that. So we can write 1 1. So first is the payoff or utility of the player 1, and the second element is the utility for the player 2. Similarly, we will not use bracket here, and here both of them utility is 0.5. So for the player 1 here, realize the outcome n comma r, and player 2 realize the outcome also n comma r. So both will get 0.5 here 0.5, and here the both will get 0.0. So this is the way of representing a game in a normal form, in tabular way. So this is called the normal form representation of the game that we have present here in the row in the row I am denoting the action of player 1 n and r. In the column I am denoting the action of player 2 and each cell is representing the utility of player 1 comma player 2. Now here we can see a simple property. So this is, if you see that since the accents are same and and the utilities or the preference is also same for player 1 and player 2, so that is why this game is a symmetric game. This game is a symmetric form game. So if we know the utility of player 1, we can easily say that the same utility will be represent the preference for player 2 also. So that means for the symmetric form game we can write this tabular form into a matrix, which is called the P of matrix. The P of matrix for player 1 and player 2 will be same for the symmetric game. So here we can write in the matrix form NR and NR, where the again the column strategy is represent for player 2 strategy and row strategy is represented the player 1 strategy. Now P of matrix of player 1 is, so here if both of them showing the action NN, that means both of them exerting force towards the nest, then the player 1 will get a payoff, or player 1's utility is 1 if n are players 1 utility is 0.5, if r and n then 0.5 and 0 0. Here r and n means if player 1 exerting force towards random direction and player 2 in the in the nest, is that is what is r and element means, and if this outcome utility is represented by 0.5, that's why I write a number 0.5. So this is called the P of matrix of the player 1. Why I am representing the player 1's utility in matrix form of every outcome. Similarly, the player, since the symmetric form game, the P of matrix for player 2 also can be written in the same way. So that will be the same as 0.5, 0.5, 0, and these are representing NR. Is representing NR here for the when this is player 1, this is player 2. Now in case of player 2, I am representing the player 2's action in the row. So player 2's action is N and action is R, and in the column I am representing here the player 1's action. So this is what a normal form game is. Now that is it for the today's class. In the next class we will see how to analyze these games in different concepts. So as we know that since the player 1 does not know what player 2 will do and player 2 does not know what player 1 will do, so and since their decisions are intertwined with each other action, so it is very crucial to extend this situation in the decision making under uncertainty. And as we know, the decision making under uncertainty will give different result as far as we know from our previous classes, that there are two basic concepts to represent decision making under uncertainty. One is VNM utility or VNM expected utility, another is procedural rational way. So in both the way we will see that for some game the outcome and the question outcome will depend on what in which way I am analyzing the game. And another thing is what does the outcome means here, so that we also learn in the next class. So that's it for the today's class.